We'll move on to the third talk of this session, which is coming from the University of Witwatersrand, or let me just pronounce it properly, Witwatersrand, South Africa. The topic is optimization of CO2 capture process by fixed site carrier membrane, and the presenter is Natsai Chiwaye.
Good day. My name is Natsai Chiwaye from the University of the Witwatersrand, Johannesburg, South Africa, and I'll be talking about the optimization of CO2 process by fixed site carrier membrane from coal power plants. In this study, we seek to simultaneously optimize the pressure and temperature. I'll take you through an introduction, then I will describe how we developed the model, and I'll share some results and conclusion. In the figure shown in the slides is a simplified block flow diagram of post-combustion CO2 capture from a coal-fired power plant. In the beginning, you have coal and air that burn, and then that burn in the boiler, and then water is changed into steam. The flue gas that exits the boiler is further treated, and then at the CO2 separation point where CO2 capture occurs, the CO2 is separated from the flue gas, of which the other components are mainly nitrogen, because of the air that has been fed to the system. So you have a high percentage of nitrogen and a low percentage of CO2. The capture process, as has been shared previously, can be achieved by absorption, membrane technology, gas separation membrane technology, absorption. The CO2 that is highly pure, like 95%, which has already been alluded to, can be stored or utilized to form useful chemicals. However, there are challenges that are faced by CO2 separation using membranes. For instance, the CO2 content is low and the flue gas is at a low pressure. However, gas membrane separation is driven by a high CO2 partial pressure. So because the inherent high CO2 partial pressure is low, you need then to compress the gas and that is consuming electricity which has been produced by the CO2 by the power plant, and it penalizes the efficiency. It further penalizes the efficiency of the power plant, and compression also increases the cost, electricity cost, and increases operational cost. Therefore, you are increasing the cost of the overall power plant with CO2 capture, and you are penalizing the efficiency at the same time. To address the challenges that I have mentioned, you need highly effective membranes that give high CO2 permeance as well as CO2 selectivity. And you can also address this challenge by systems process engineering and optimization. One such membrane that exhibits high CO2 permeation is a fixed site carrier membrane, such as polyamine membranes. And shown in the figure is how the CO2 is transported through the membrane, where the initially CO2 reacts to form a carbamate and finally bicarbonate ion, and this further generates at the end of the membrane to give back CO2. The reaction occurs in the presence of water. Therefore, you are introducing more parameters that need to be controlled when you are operating the system. So you need a humidified gas for the CO2 permeation to realize a high CO2 permeance. So in modeling the CO2 permeation through fixed site carrier membranes, normally we tend to just assume that the CO2 permeance is constant. However, the the CO2 permeance is not constant along the membrane profile, since water is also permeating through the membrane, and that is changing the composition of the water. The concentration of the water within the membrane profile is changing. When you saw the figure on, it shows that as the CO2 partial pressure is decreasing, the CO2 permeance also decreases. So along the membrane profile, the CO2 permeance is not constant, it is changing. As you also increase the feed pressure, the CO2 permeance decreases. However, for a normal polymer without amine groups on it, the permeance is constant. Therefore, you can assume constant permeance across the membrane. By assuming a constant CO2 permeation, you are not accurately capturing the system that what is occurring within the system accurately. In the table shown are some relevant modeling studies that are in the literature, starting with here like in 2014, where they assumed constant CO2 permeance, and initially they would assume a high relative humidity because the CO2 permeation is optimum in a humid environment of about 90%. So initially you'd say the feed gas is at 90%, you feed it at least 90%. However, within the membrane profile, the relative humidity is decreasing, but you assume that the CO2 permeance is just constant, it's not being affected by that decrease in relative humidity. In our previous work, we assumed a variable permeance, we assumed variable permeance, and we assumed a fixed membrane temperature. However, a study in 2021 gave a model for how the membrane operating temperature is affecting the CO2 permeance. And therefore, in this study, we seek to further build on to see if there is any reduction in cost when membrane operating temperature is considered. So the objective of this study was to develop a superstructure-based optimization model for the capture of CO2 by a fixed site carrier membrane from multi-component saturated flue gas from a coal power plant. And sought to optimize the membrane operating pressure as well as temperature and optimize the target cooling temperature of gas streams. To do this, we are given that we know the flue gas flow rate, the composition, the temperature, and there are some set product purity and desired capture ratio that's a standard that is used in literature, such as recovery of 90% that has already been shared in the previous presentation, and the product purity of 95%. And in the process, we sought to determine the optimum process that results in minimum total annualized cost, the optimum process conditions, such as the optimum pressure of the membrane stages, the membrane area, and the membrane operating temperature. Shown in the figure is the superstructure from which the model is developed. And the superstructure shows that flue gas is supplied to the power plant, and it can be split and can be sent to any of the membrane stages that are presented. It also shows that the permeate streams can be recycled, and then the retentant streams can be recycled. These are mixed. The flue gas can be mixed with the recycled streams. However, the superstructure is designed such that the streams are mixed at the same temperature and pressure because of the challenges that are associated with algebraic-based optimization platforms. And I was happy to learn from the lecture yesterday that's through the ideas projects, there's work that is being done in order to incorporate thermodynamic properties as well as an equation of state into these modeling systems. So in the future, we will not have to develop the superstructure where we have to cool down streams or to compress them so before we mix them, so that they are mixed at the same temperature and pressure. So some assumptions that were done for the model is to assume negligible pressure drop along the membrane profile. The model was developed by assuming counter-current flow pattern. Then permeation of the CO2 was varying with the CO2 partial pressure across the membrane. Then there were material balances carried out around mixers, heaters, and other constraints such as membrane area range, capture targets, pressure range for permeate sites, then equipment duties, compressors, expanders, vacuum pumps, then coolers, where there's an option that water can condense depending on its composition. The objective function was to minimize the total annualized cost, which is the sum of the capital cost and operational cost. The model was implemented in games and solved by Aaron. The example that we sought to use was this example by he and Heck in 2014 in their simulation study. The power plant that was considered in the study was a power plant that produces 819 megawatts of electricity. The CO2 emission was 763 kg. The plant gas flow at 26.61 kilometers. These are the cost parameters that are taken from the same literature source. The results and discussion for analyzing how the model performed, we carried out 3 optimization runs based on these 3 scenarios. The first scenario was from the previous work where we had temperature as a parameter. And in this instance, the membrane operating temperature was assumed to be 388 kelvins. The second scenario considers a uniform temperature in all the membrane stages. Then the third scenario allowed temperature to be non-uniform depending on the membrane stages. All optimization runs were carried out based on 3 membrane stages. And in all instances, pressure was allowed to be non-uniform in all the membrane stages. Shown in the picture, in the table, are the pressure ratios that were realized based on the optimum retentant pressure and permeate pressure given. And then the feed relative humidity is also shown. It shows the results show that for the non-uniform temperature optimized scenario, then you have an opportunity to, the optimum permeate pressure is low atmospheric at 1 bar. So the other 2 stages are operating at atmospheric pressure without vacuum operation. For further more results, the table shows that the membrane area is increasing as temperature is becoming is allowed to be a variable that is optimized in the system. Because temperature is being optimized in membrane temperature is being optimized in the system, the total net power for the 2 cases where temperature is being optimized decreases. The effect on the cost is however small, at maximum 4.6%. So it is beneficial to make temperature a variable. However, the benefits are not very good. Results and discussion. In the literature before, it was also shown that there's a low variation in permeance with membrane temperature. We have optimized the membrane process for CO2 capture from a coal-fired power plant. based on a humidified multi-component flue gas while it's optimizing membrane pressure and membrane operating temperature. The optimum conditions results in energy savings for both scenarios that involve temperature optimization. However, an increase in membrane area was noted. I acknowledge the interest of the Vet Waterstrand Research Office. Thank you.
Questions for the speaker?
Just to understand the requirement of membrane for this CO2, requirement of the membrane for this flue gas in order to extract CO2 for this carbon storage. Because our intent, or you may clarify with me, the real requirement of storing all this CO2 is basically the whole flue gas. So what is the real intent that we want to separate first, then only we are storing this CO2? And if we are doing that, and what will be the location of all the residual that we are getting from the membrane as a product?
Okay, thank you for that. In our study, we did not consider transportation and storage. We just considered the cost of separating CO2.
So what is the intent of separating that?
That it may be transported and then further stored or utilized. So it would depend on what the person or organization that uses our data intends to do with the CO2. Then they would carry out further analysis to analyze the cost of transport to a storage site or utilization, or whether that is going to occur on site, then you don't have transport costs.
Just to understand, because from the membrane we have a product, we have the permeate. So I just want to understand what is the intent or to purify, and what will be the solution for the residual, which is actually the product from the membrane as well, isn't it? So I just want to have an idea on that. It's okay. I mean, if it's more on the membrane to separate the CO2, it's fine. Just want to have a global overview on the carbon capture storage that we are trying to apply in the industry, because our concern is more on it is not necessarily to have very pure CO2. Our requirement, whichever that have very high CO2, we have to store it. So there is a new regulation start coming into industry. So there's a reason I'm asking. Thanks.
And to talk up from what Anwar has said, the main issue with carbon capture is the compression cost. The cost is simply too high. In research, we always try to optimize this, optimize that, but when we really want to apply this for carbon capture, especially for oil and gas application, the operating cost itself is the main limitation that knock them down. So unless we can find something to address that, this carbon capture is not going to be immediately available, at least for a short time, unless there is a big incentive given by the government. Yeah, maybe a quick one.
Yeah. What are the operating temperatures of the membranes in your case?
For the optimization, for the temperature optimization, we use it 20 to 60 degrees.
So, but then it means that you are going to condense water. Is part of it.
The water that is condensed from the downstream streams, like the permeate stream, after it leaves the membrane.
But when it enters the membrane, so if you have to cool it down, you've already lost part of the water, no?
Yes, you are losing the water, but you are also feeding, you are also compressing at the same time. So when you're compressing, then you have a higher pressure, and then the relative humidity will be high. But in the model, we set constraints that fix the feed relative humidity to at least 90%. So there are equations there that make sure that the feed is always at least 90% relative humidity.
Yes, there is no liquid. You have separated part of the water.
Yes, but we allow some water to always be in the system. Using them.
Just a quick question, what was the optimal temperature? You said range is 20 to 60. What was the optimal value? The temperature is optimized.
I have the optimum membrane, temperatures for the different regions.
These are already optimal. Okay,
Yeah.
thank you.